Hello, everybody. My name is Laxmi. I'm a research fellow at the University of Michigan. So the talk I'll be giving about is the work that I did during my PhD dissertation research under the guidance of Dr. Zhang Shah. So basically, as we know, customer demand is changing. Can I remove this screen out of the way real quick? So customer demand is changing where they're requiring more and more customized and personalized products. Manufacturing is trying to catch up, but still based to this traditional line-based manufacturing where things are basically set up in line in sequences with standard processes that has mass manufacturing thrive. But this approach of manufacturing is rarely able to match the changing demand of customized product. That is where this concept of swarm manufacturing comes into consideration. It's basically the novel paradigm for distributed manufacturing where networks of micro factories are established at different geographic locations to enable on-demand manufacturing. It does so by enabling a group of heterogeneous robots that work together to manufacture a variety of different products at each of these micro factories. And as it can be seen that it has several benefits, both in terms of economic as well as societal aspects. So in terms of economic dimension, we can see the current state of supply chain has been really disrupted with a lot of different factors. And if we had this, individual microfactories at certain geographic locations, people that need any kind of product can be manufactured locally with using different local dimension, which significantly reduces this complicated supply chain that are very fragile at this point. And on the other side, it also has a lot of societal benefits because it promotes use of local products for manufacturing, as well as promote entrepreneurship and so on. So cooperative 3D printing is a primitive form of swarm manufacturing where basically all these cooperating robots are mobile in nature and do primarily 3D printing. Such cooperation is achieved by using the concept of this new concept called chunk-based printing, where we divide an entire part into multiple smaller chunks, as we call it, or smaller pieces, if you will, using a chunking strategy so that the chunks can be assigned to individual robots, which can then work in parallel to print the assigned chunks. Since prior to this one, there's no existing approach that allowed us to take a big part and just take a model of that object and assign to multiple robots for 3D printing. So we discretize this entire process of 3D printing using multiple robots into multiple stages. The first step is basically taking this part and discretizing into smaller chunks. And so in this case, we use some sort of chunking strategy to divide the part. Once the part is divided into smaller chunks, we then create a print schedule, which basically includes chunk assignment as well as sequence generation, which can be represented using this directed concept of directed dependency tree, where each of these nodes represent a chunk, and the edge connecting two nodes basically represents the dependency relationship going from chunk to chunks, basically. And once the schedule is generated, we do path planning and motion planning and basically implement the print schedule to print the part. So the first step of this cooperative 3D printing is chunking, which is, like I said, a process of dividing a given geometry into smaller chunks so that they can be assigned to individual robots. However, it's somewhat different to the conventional geometric partitioning problem as it requires some additional consideration. For example, chunking should allow simultaneous multi-robot printing, right? That's how we reduce it all the time. And the bonding between the chunks should also be formed while the printing is taking place as well. We cannot wait until all the chunks are printed and then have somebody else come and glue the part together. So to achieve this objective, we introduced a concept called slope surface chunking strategy, where planes at an angle are used to partition a part into multiple chunks, as shown in the figure here. The chunking is done along one axis first, in this case x-axis, and then along another axis, resulting in multiple number of chunks. So in this case, there are 30 chunks in total. And the figure at the bottom shows how the addition between the chunks takes place as the heated nozzle comes in contact with already printed chunk here, right here, and it deposits new material. The heated nozzle, softens the previous material, and the contact between the two material takes place, and the addition is created right there. We've studied some mechanical properties of this chunk-based part. I'll be happy to refer any of the previous studies that we've done, but these are not highlighted in this presentation. So the second aspect of the cooperative 3D printing is scheduling, which includes chunk assignment to the robots, printing robots, and generating print sequence to undertake such printing. So if you look at this, same rectangular board that I showed previously, and once a parted chunk, we can represent the print schedule using a directed dependency tree. In such representation, all the chunks in the same row gets printed together, as shown in here, and all the chunks in the same column. So there are 4 columns in total. Each of these individual chunks, each of these individual column of chunks are printed by one robot. So for example, a single robot prints all these chunks, this one, second one prints this one, and so on. So in addition to this, we also, while generating such print sequence and assignment, we need to ensure that we avoid any kind of conflict. Right? This conflict could arise due to some sort of chunking strategy, or it could also arise due to robots are printing different parts, and want to make sure that when they travel from one location to another location, they do not collide with any other printed part. And also want to make sure that during any print cycle, they do not collide with one another either. So this type of scenarios are to be avoided while generating a print schedule. And finally, another aspect of scheduling would be to, once you have a schedule, we're going to find out how long it takes to print the entire part, right? So we want to make sure we utilize the directed dependency tree that we use to represent the print schedule. So we formulated a mathematical formulation to kind of evaluate the print schedule to see how long each print or total print takes. I've not put that equation in here because this is a short talk, but if anybody is interested, I'd be happy to send the reference material later on. So combining these two, so combining these two frameworks, the software components or frameworks that I talked about previously, with the chunking, scheduling, simulator, just to kind of demonstrate, simulate how printing takes place, and some of the hardware development done by Ambots, a startup based in Fayetteville, Arkansas, we're able to actually demonstrate the actual printing of really large object using these 2 printers. As you can see, these 2 robots are printing basically chunks that have been pre-assigned to them. And as they need to move from one print location to another location, a mobile platform comes and picks the printer up, moves into a different location. The printer starts printing the assigned chunks again, and the process continues until the entire part is complete. So in this case, the part that was printed was about 1,000 millimeter by 350 millimeters, so it's pretty large. So as you can see, how this concept of chunk-based cooperative 3D printing can be utilized to print something really large scale. And then finally, I want to highlight some of the future direction that we could, or even the other researchers could take to further the concept of cooperative 3D printing. So we believe that this is just the inception of, we're just at the beginning of cooperative 3D printing, multi-robot printing, whatever you want to call it. And there are a lot of work to be done. And some of this, it will probably take a group effort of the whole community to further this research. Some of the potential avenues could include, in terms of chunking, this could be developing new chunking methods, or even doing a further study of mechanical properties of chunk-based part to kind of basically reinforce some of the studies that we've done. In terms of scheduling, some of the new developments could include generation of print schedules that are more agnostic to the chunking strategy, and even leverage some of the existing studies in multi-robot field to come up with new printing strategies. Aside from this chunking and scheduling, some of the other research avenues could include using layer-based printing, which is basically if you even go for discretize the entire part further down into layer-based and assign individual layers to printing robots and have them collaborate while they're printing individual layer, that could provide more control to the user. At the same time, we can even go further down to a G-code level compared to a layer level and assign each of these lines to robots and have them collaborate while they print this individual G-code line. This would provide more flexibility to the user, but at the same time, it probably require more rigorous research work in future. With that being said, that is all I have. I'll be happy to take any questions.